I got early access to Kimi K3 a few days ago before it went public. I've been running it for the last few days, and before I show you what I actually tested it on, I want to walk through what this model is, because the parameter count is very interesting to say the least. Here's the real question I want an answer to, and it's bigger than just this one model. Can a frontier model actually reproduce a novel machine learning paper from the mathematics alone, with no reference code, with nothing it's already seen 1,000 times in training? Every launch this year gets tested the same way. Build a game, build a website, look impressive for 30 seconds. Almost nobody asks whether these things can take a paper they've never seen implemented anywhere and get the math right on the first real attempt. K3 is just the first model I'm running this question on. Kimi K3 comes out of Moonshot AI, the team behind Kimi K2, Kimi 2.6 and 2.7, which were already very solid open weights models. The headline number on K3 is 2.8 trillion total parameters, which makes it the largest open weight model released so far. But total parameter count on its own doesn't really tell you much. The number that matters most is active parameters per token, meaning how much of that model is actually going to do work on any single answer. Kimi 2.7 sits at 1 trillion total with 32 billion active. GLM 5.2 is smaller overall, at 753 billion total. But its active parameter count is a lot higher, and that's a big part of why GLM 5.2 punches above its total size. So with K3 at 2.8 trillion total, the question isn't whether it's big, it's whether Moonshot pushed the active parameter count up along with it, or just scaled the total and kept the same parse ratio as before. If it's the second one, K3 gets more knowledge backed in without necessarily getting smarter per token. The architecture rumor is that K3 is an ultra-sparse mixture of experts model, using a hybrid FMLA and KDA style attention. Moonshot has already published research on this kind of linear attention approach. The point of that combination is to let the model carry much bigger total capacity without making every single response cost as much as a fully dense model that size would. That architecture is also what's expected to give K3 a 1 million token context window. The catch with any 1 million context model is routing. When you have that many experts and that much context, a bad routing setup can make the model mildly inconsistent. It might nail one coding task and then pick up the wrong experts entirely on the next one and lose the thread. That's actually shown up before in Kimi's own agentic coding rankings on Agent Arena, where Kimi 2.7 code sits around rank 20 and Kimi 2.6 around mark 24. Agent Arena isn't a static leaderboard either. It tracks real agent behavior over time using signals like downloads, disapproval, retries, and how steerable the model is mid-task. So it's a decent proxy for whether a model can actually hold it together across long coding sessions, not just answer one prompt well. There is also a rumor going that K3 might be actually a distilled version of Fable 5. Nothing confirms that, and I'm not going to pretend it's settled. But it's worth mentioning because it shapes expectations. Fable 5 is genuinely excellent in planning and reasoning, arguably ahead of GPT 5.6 Soul on that front. But it's not particularly strong at raw coding output on its own, which is why a lot of workflows pair Fable 5's planning with a stronger coding model. If K3 inherited any of that reasoning strength while also being tuned specifically for coding and tool use, that would be the best case scenario. And the more grounded comparison, though, is against GLM 5.2 Max, since that's the open model K3 actually has to beat to matter in this tier. If Moonshot gets the routing right and the active parameter count scales with the total, K3 would easily fit in the top 10 on Agent Arena, possibly closer to GLM 5.2 than the closest frontier models. If it undershoots on routing, you'll see the same pattern Kimi has had before. Flashes of very capable model that falls apart on longer sessions. That's the context. And now, here's what I actually did with my access. Like I said, most launch videos this week are going to show you K3 building a game or a 3D scene, and that's a fine way to see the vibe of the model. But it doesn't tell you much about whether it can reason through something with a right answer at the end. So I wanted a test where I already know what correct looks before I start, and where the question being answered isn't just about K3, it's the question I asked at the start. Can a frontier model take a novel paper and rebuild the math correctly with nothing to copy from? Before I get into the test, let me explain what this paper is actually about. because the terms KDA and MLA are going to come up a lot, and I don't want to throw jargon at you. Every time a model like this generates text, it has to look back at everything it's already written or read to figure out what comes next. That's what attention does. The normal way of doing this, called full attention, means the model keeps a running record of every single word it has seen so far. And every time it writes a new word, it checks that new word against every single one of these old words. If you've written 1,000 words, checking the next word costs you 1,000 comparisons. If you've written 1,000,000 words, well, it costs you 1,000,000 comparisons. And that record it's keeping in memory grows the same way. That's why models slow down and eat more memory the longer a conversation or document gets. The cost grows much faster than the text does. Kimi delta attention, or KDA, is Moonshot's attempt at avoiding that problem. Instead of keeping a full record of everything and checking against all of it every time, KDA compresses what it has read so far into a small running summary, and it updates that summary a chunk at a time as it goes, using a gating mechanism, which is just a set of rules for deciding what's worth keeping in the summary and what can be dropped. That's why the style of attention barely gets more expensive as the text gets longer, since it's not comparing against everything. The trade-off is that a pure summary-based approach like this can lose some fine details, so of course Moonshot didn't go all the way in. Kimi Linear uses a 3-to-1 mix, 3 layers of the cheap summary-based KDA for every 1 layer of the expensive, but more precise, full attention. The full attention layers act like periodic check-ins that catch everything the summary might have smoothed over, while the KDA layers do most of the heavy lifting capabilities cheaply. That's the whole idea. Cut the cost of remembering long text by mostly working off a compressed summary instead of the full history, and sprinkling just enough full attention to keep it accurate. Moonshot's own numbers claim up to 75% less memory spent on that running record, and up to 6 times faster generation at the million token range. This paper works as a test case because it's recent enough, math heavy enough, and specific enough in its claims that there is no faking a correct answer. I gave K3 this paper and nothing else. No reference code, no repo like I said, and no browsing access. So, here's what K3 actually has to do. First, implement the KDA layer from the paper's math alone, the chunked recurrence update and the gating. Nothing else. Then I check it the same way you check any kernel implementation. Run identical random inputs through K3's version and through Moonshot's own open-sourced reference kernel, and see whether the outputs match within a small numerical tolerance on both the forward pass and the gradients. Getting a gated linear attention mechanism with chunked recurrence to match a reference exactly is a genuinely hard problem on its own, with no training required. Once it's numerically correct, I test the actual efficiency claim the same way the paper does. As a property of the mechanism itself using random, unconstrained weights, I benchmark K3's implementation against a plain full attention implementation at a few increasing sequence lengths, and measure memory used and time per decoded token. Full attention should blow up quadratically. KDA is supposed to stay close to flat. That shape is what I'm checking for, not the paper's exact 75% or 6x speed. Since these come from a scale I can't touch, no training loop anywhere in this test. This is the part where I actually care about answering, not just can K3 use KDA, but can it read cold math it's never seen implemented anywhere and gets it right. So, here are the rules. No reference implementation. Even if the authors published one, K3 only sees the paper. No browsing access during the task, and it has to implement the KDA layer from the math alone. No training involved anywhere. I check correctness by diffing its output against Moonshot's own open-source reference kernel on random inputs. Once it's numerically correct, I benchmark memory and decode speed against a plain full attention implementation using untrained weights. And I'm timing everything and logging every point where I had to step in. Kimi thought for 40 minutes while reading the paper. And then, verification came back first. It made 6 test cases, checking the chunked implementation against the raw recurrence in float64. Different sequence lengths, ragged sequences, with and without a starting state. It failed multiple times, but at the end, all 6 passed. The relative error around 10 to the minus 14 to 10 to the minus 15 on the output, the final state, and the gradients, which surprisingly pushed the precision limit of float64 itself. The chunked math K3 wrote is an exact match to equation 1 in the paper. The benchmark compared KDA against plain full attention. Same model size from 1024 tokens up to 32,000. Full attention's decode time per token grew almost 16x over that range. Its cache grew 30x, which is what quadratic scaling looks like in practice. KDA's decode time per token moved about 2%. Its state size stayed at 0.5 megabytes the entire way, at 1,000 tokens and at 32,000 tokens. The flat line is the paper's central claim, a fixed size running summary instead of a growing history. The absolute numbers here won't match the papers, since this is an optimized Python on a single consumer GPU, but the shape of the two curves is what I was checking. And it lines up. So back to the question from the start. Given only the paper, no reference code, K3 got the math right on the first attempt. It matched the reference kernel to near machine precision and produced its scaling behavior in the same direction as the paper. And it used 30% of my 5-hour limit on the max plan. And that's K3, beta tested a day before public release. I'll put the reproduction code and the full run logs in the description so you can implement it yourself. So let me guys know in the comments if you want me to make a series about this test. Bye bye!